For today's lesson, we're going to be looking at section 1.1, which is basic concepts. Your essential question for today is, what are some concepts that serve as a basis for algebra? One of the first objectives in Unit 1 is to look at our number sets. Now, you guys have seen these before, and all these words should be familiar, but you're going to be tested on these, and I want to make sure that our vocabulary is where it needs to be. I'm going to start, if you follow my red laser, I'm going to start down here with the natural numbers. Now, the natural numbers are the ones that are natural to count. If I would say count to 10, you would say 1, 2, 3. 4, 5, 6, etc., etc. You wouldn't say 0, you wouldn't say fractions, you wouldn't say decimals, because they're not natural. So when you think of the natural number set, I want you to think of the ones that are natural to count. This is an infinite set, as it will go on to positive infinity. The whole numbers is the second set of numbers that we're going to look at, and the whole numbers include the 0. So they're the natural numbers plus 0. And the way that I want you guys to remember this is when you say whole, your mouth forms a 0 or an O, including that 0. Once again, these do not include fractions or decimals. Whole numbers are 0, and then the natural numbers. Looking at our third sets are the integers. And integers, the definition of an integer is a number and its opposite. So basically integers include now the negatives, the 0, and the positives. So we're finally looking at including negative numbers. Now this will go all the way down to negative infinity, negative 1, negative 2, negative 3, all the way down to negative infinity. It will also go up to positive infinity, 1, 2, 3. Integers, once again, for the third time, we're not including decimals or fractions yet. We are just talking about whole numbers, integers, natural numbers. Rational numbers is the third set, and rational numbers includes any number that can be written as a fraction. So a rational number can be any number that you can put into fraction notation as a ratio. So any of the natural numbers can be written as a fraction. Put them over 1, any of the whole numbers, any of the integers. So rational numbers include everything underneath it, because everything underneath a rational number can be written as a fraction. They also include terminating or repeating decimals. What do I mean by a terminating and a repeating decimal? Well, a terminating decimal is a decimal that stops. For example, 0.5. 0.5 is 1/2. That can be written as a fraction. Or a repeating decimal, 0.33333333. Well, that's 1/3. That can be written as a fraction. Over here, we've got your irrational numbers. Irrational numbers basically is everything else. Any number that cannot be written as a fraction. So that would be your non-terminating or your non-repeating decimals. For example, pi. Pi doesn't repeat, but it doesn't stop either, so it would be irrational. It would also include some of your funny square roots. Square root of 2, square root of 13. Everything in this box is a real number. Everything that we're going to talk about is a real number. What is not a real number would be your complex number system or your I's, your imaginary numbers. We're going to deal with that later. But everything that we're going to deal with for the first several chapters of college algebra is going to be a real number, and it can fall into any one of these 5 categories. The next objective of Unit 1.1 is set notation. And set notation is something that looks similar to this, and you have seen it before. But now we're going to focus on being able to read it. So set notation looks like this, and what it's representing is what's right here. This is representing the set of all x's such that x is greater than or equal to 5. So in other words, we're saying any number that's greater than or equal to 5 follows into this set. This is called set builder notation, and let me explain how to read this. This brace right here means the set of all . This x right here stands for x's, the set of all x's. This vertical bar stands for just such that, the set of all x's such that, and then this stands for x is greater than or equal to 5. So this would read the set of all x's such that x is greater than or equal to 5. This is a very fancy way of representing the set of numbers that fall under the category greater than or equal to 5. Any number greater than or equal to 5. And this is how you would read that. Last but not least, we're going to look at something called interval notation. Interval notation is new, unless if you had me for Algebra 2, you haven't seen it, because it's not taught below the college algebra level. So interval notation is just a different way of graphing and writing a set of numbers, and you'll be asked to do it throughout the entire year of college algebra. So we need to make sure we learn it now. Let's say that I go back to the set of numbers that we were just talking about, the set of numbers greater than or equal to 5. Now, if you were in any lower level class and I asked you to graph that, you would pull out your number line, you would put your 5 on it, and since it's greater than or equal to, you would have put a closed circle, because that was underlined, and greater than would be all the numbers to the right, greater than or equal to 5. So this would just represent this set of numbers, all the numbers bigger than or equal to 5, all the numbers bigger than or equal to 5. We are in college algebra, so we were not going to use this old way of graphing. We're going to use a new way of graphing called interval notation. There's two pieces to interval notation. The first is the graph. So this still reads x is greater than or equal to 5, but instead of a closed circle, in interval notation you use a bracket. And I know that I need to use the bracket because this symbol up here is underlined. The same way we knew to do a closed circle because it was underlined, we know to do a bracket because it's underlined. Same thing. And since it's greater than, we would go to the greater than. So these graphs would be comparable in the same thing, but once again, in college algebra, this is how I would expect you to graph this, no longer this. The only difference is you used a bracket instead of a closed circle. Now the second component to interval notation is actually writing what that number set means. And what I need you to do when you write interval notation is I want you to think of smallest and largest, and it will always go in this order. What is the smallest thing that x can be? If I'm looking at this set of numbers, what is the smallest thing x can be? Well, the smallest thing that x can be is a 5. In other words, if I'm trying to go, this is my set of numbers, and if I'm trying to move to the smallest number possible and I'm moving my laser down here, I am stopped by that 5. The smallest number my x can be is 5. What's the largest thing x can be? Well, once again, if I'm taking my laser and trying to go to the biggest number possible, it's going to go on and on and on forever. So the largest thing x could be would be infinity. Now we need to border these numbers, so what we need to do is, since the 5 is put in a bracket right here, I'm going to put my 5 in a bracket down here. Infinity and negative infinity are always bordered by parentheses no matter what. So what you're doing here in this interval notation is you're telling me the set of all numbers such that 5 to infinity. And you're also telling me by this bracket that 5 can actually be part of my number set. It's okay to be 5. This bracket comes from this bracket, follows from this being underlined. They're all tied together. Let's go ahead and look at a different set of numbers. So if I'm reading this appropriately, this is the set of all numbers such that x is less than 2. So if you guys remember when we talk about set notation, x is less than 2, right here is the important part. If I ask you to write this into interval notation, there are two components. If you'll remember, the first one is the graph. So the first thing you want to do is set up your graph with your 2 in it. Now since this is less than, we're now going to be going in the left direction, whereas before it was greater than or equal to 5 and we went in the right direction. This is less than, so we're going to go in the left direction. You'll also notice this is not underlined, and because this inequality symbol is not underlined, the way that we represent that is with an open parentheses. So before, on our previous slide, we used a bracket when it was underlined. When it's not underlined, you use a parentheses, facing in the direction that you need to be going. The second component to interval notation is to represent the numbers in a almost like an ordered pair. And if you'll remember, we talked about always going in the order of smallest to largest. That'll be the same every single time that we do this. So if I'm looking back up here at my graph and I want to see what the smallest thing x can be is, we're going to go in the left direction, because remember, we get smaller as we go to the left on a number line. So 2, 1, 0, -1, on and on to negative infinity. In this case, the smallest thing that x can be is a negative infinity. And then if you go back up, the largest thing that x can be, so once again, looking at our graph, when we're looking at the largest thing, we go to the right. Well, it's going to stop me right there at a 2. I can't be any bigger than a 2. Now we need to border these, and we know that infinity and negative infinity is always bordered with parentheses. Now the 2 is bordered by parentheses as well, because it's bordered by parentheses right here, because it's not underlined right here. So once again, they all tie in together. So this is not underlined, so it's parentheses here. This is parentheses here, so it's parentheses here. These all go together.